Hello everybody, my name is Connor. You may also know me as Katabatic, C-State, or a few other names, Kata. I have been working on a operating system that I've been writing it from scratch, and this is just going to be kind of a devlog, kind of just talking about my project, talking about its structure and how it works. Maybe if you're working on an operating system of your own, then you might learn a thing or two from what I've been doing. This is going to be a kind of unedited, just raw, uncut video. So apologies if I stumble over my words occasionally, or if I kind of slow down and gather my thoughts. I'm not doing this with any kind of script or anything. This is literally just me brain dumping about my project that I've been very passionate about for the past few months now. So this particular iteration of my operating system, which is called k4dos, stands for Kata's operating system, or Katabatic DOS, or whatever you want to call it. This version that I have pulled up here in VS Code is the, I want to say, fourth version of the operating system that I've started over from scratch with. When I first started out, I used a very good resource about writing an operating system in Rust that I'll link in the description if I remember to. So so k4dos is written in Rust. It's written almost entirely in Rust. The only parts of it that are not Rust are the inline assembly and naked assembly Rust functions that are embedded within the Rust source code itself. I guess you could also count the build scripts and the linker file as part of what's not written in Rust. In fact, let's do a quick lines of code in here. I've passed 8,000 lines of Rust code. So, yeah, written almost entirely in Rust. Then the next highest is Bourne Shell, which is probably just my build scripts that I have. There's a little bit of C, mostly for testing various applications. Or testing various functionality from C. And yeah, so I guess the best place to start is to get right into it. And let's open up main.rs. So this is built on the nightly version of Rust, of course, because you kind of need to if you're going to be using any of these features that I have in the features tag. So split up into a few different modules, but this is all of main.rs. And so the actual entry point to Rust is called from the bootloader. And as you can see, I think up here somewhere, I don't even have it in this import into main.rs, but the bootloader I'm using is Limine, or Limine, or Limine, or whatever you want to call it. The kind of thing that uses this kind of configuration file. I like Limine. I just started using it recently with this project, with this most recent rewrite that I've been working on for about a week. Yes, I've written almost 9,000 lines of code in a week. Come at me. But I want to stress again that I've worked on this 4 different times. So this is my 4th try, basically, at making an operating system. This is one that's come the farthest. And I'll talk about the reasons for that later on. So, yeah, so Limine is my bootloader that I've been using. I found it very easy to implement and integrate. I only need a few different features from it in order to in order to get it working, in order to get my kernel up and running. So as you see in main.rs here, we have a static for the physical offset. This is given to us by Lamine for the physical offset of where the kernel is loaded into memory by Lamine. So, and then the start point, entry point from Rust, or into Rust from Lamine is right here. You see we just call an architecture specific main function, which k4dos only supports one architecture right now, and that's x86-64. It's been a lot of, I guess you could call it fun, to learn how x86-64 works by working on this project, but either way, let's go and jump right into there. And see, now we got a lot more going on. So apologies if you can hear my laptop's fan running very loud. It's probably going to be happening a lot throughout this video. So we get a few different requests from Lamine. In fact, we don't even really use some of these. Yeah, the memory map I think is used to initialize the frame allocator. Yeah, it is. Okay. Some of this code I haven't looked at in a little bit, so this is my first time actually going through and stepping through the code in a while, or ever, I think, actually. I've just been adding features onto it, and this is going to be a good review for me to be able to, what was I going to say? Like figure out what's going on and figure out what I want to work on next with it. Because I'm kind of at that point right now where I don't really know what I want to work on next. So, first things first, we disable interrupts. I mean, yeah, that's pretty standard to initialize all your memory and everything with interrupts disabled. It's, because you don't want to be catching interrupts when we don't have an IDT set up or any interrupt handlers or any of that. So disable interrupts. I'm just gonna skim through this, and we can go into it in more detail. So we get the memory map from Lamine. We store that physical offset into the atomic, the global atomic. We initialize our logger. I use a logging crate, a pretty standard one, just called log. And then the logger actually uses a serial interface to log to my standard output in my development environment. I don't even know why that's there. You're going to see lots of little commented out lines of code in here. I haven't cleaned those up yet for this video. I figure I just wanted to get into it. So might be cleaning up the code a little bit as I go. So we initialize the logger. We get the kernel elf binary from Lamine. Excuse me. And we store that in another static so that we can get backtraces from the kernel's symbols in the panic messages. And those have come in very much in handy. I guess now's as good a time as any to say that a lot of this code is based on other projects. So originally, sorry, this is all over the place, but k4dos was originally based on referencing the source code of a project called Kerla. It's kind of the first operating system in a Rust project that I tried to kind of follow along with. I've also taken inspiration from projects such as Theseus and Redox, and most recently Aero. And this latest version has a lot of code that's really inspired by Aero and how it does things. So, although there are bits and pieces of inspiration from each of those projects in here still. So, this backtrace with the kernel elf is from Lamine is inspired by Aero and how it does it. So, initialize some floating point unit mechanisms, such as xsave, mmx, sse, etc. We assert that we have that functionality to begin with because it is kind of important for how k4dos works and how the kinds of programs that it can load kind of need that functionality. So, and then we set up our xsave and all that and blah blah blah. Set up our CR4 registers, our CR0 registers, to make sure we have all that all set up. We initialize a boot time or a initial boot GDT, global descriptor table. That's another x86 thing that I'll get into maybe in a bit. We initialize our frame and page allocators for the kernel. There's actually only one frame allocator. It is the kernel one because that's the one that allocates our physical memory, and we need to know the memory map of our system in order to do that, and we get that from the mine. So after that, we create a new page table, a new level 4 page table to use for the kernel and the kernel's idle task and the kernel's, the kernel's threads and stuff like that. After that, we set up the kernel heap so we can use the alloc crate in order to use some handy collections that are used throughout the rest of the operating system. This is an internal thing with my allocator that I've made. It is able to either be statically allocated with a static limit on how many allocations it can hold, or it can be heap allocated, and it can convert between the two. And I'll get into that. That's kind of neat how it's set up. That was inspired by Theseus. Set up syscalls and all the stuff we need for user mode to work properly. We load an actual GDT that we're going to be using for the rest of the boot time, for the rest of the uptime of the operating system. We load an IDT for interrupts. We initialize our file systems. We initialize our task scheduler. And then we start up our init process, which right now is pointing to cache, which is my custom shell that I've written for k4dos. It is also written in Rust. I'll get into that at the end, probably. Set up some file systems, some devfs stuff like null and tty, so we can communicate with the user. And we log welcome to k4dos. So yeah, here's where we actually start up the init process. This just loads it, but this is where it actually starts up. It's pushed into the scheduler as a runnable program, as a runnable task. And we also start up a kernel thread to pull the serial 1 input, basically. And so I use 2 serial ports in the emulator in QEMU. One is for logging, for like the equivalent of like your D message in Linux, and the other is for actually communicating. Sorry, that was my phone. Let me silence that real fast. My phone might go off actually, but it's fine. I'll just throw it over here. There it goes, on my bed now. So, and then after we set up all of our stuff, we enable interrupts, and the scheduler will take it from there. So let's go into each of these in a bit more detail. First things first, this is just checking that our stack is valid, that we can write to it and all that, and or that we can read from it at least. This is something that Aero does that I liked, so I put it in there. We get our memory map, we store a physical memory offset, we already talked about that. Logging isn't super anything to be fancy about. It's literally just a serial logger that has color-coded output. Kind of fancy, I guess. So, oh come on, take me back. There we go. Freaking VS Code. So this batch is saying, this is really just kind of code stolen from Aero, but this essentially allows me to iteratively unwind the stack frame, stack base pointer as well, RBP in x86-64, and we try to load and demangle each symbol that it finds. So they'll print a nice pretty backtrace for us. And then this is our panic handler. It just says it panics. We also echo that that we panicked to the user on the serial 1 interface. And then we unwind stack and halt and catch fire. So, all right. So that's all that. Let's go back. FAQ mechanisms is kind of boring. Boot GDT, it's really just a simple GDT to get us up and running. Frame allocator and page allocators. We just, for the frame allocator, for the physical memory allocator, we take each entry in a memory map and we add its start and end to the allocator. For the page allocator, I'm pretty sure we just map both the high and low virtual address spaces for kernel to use. It gets the entirety of the virtual address space, all 512 bytes, something like that of it. So if you have 512 terabytes of RAM, then k4dos will work on your system. That's a joke, by the way. So let's talk a little more about these allocators. So I mentioned that it's able to be either statically allocated or a vector, or sorry, I call it static list or vec, but basically it's a array vec from the array vec crate with a static cap. Or a vector, and this cap isn't how many it's actually not how many allocations it can hold, it's how many free spaces it can hold. So if you've never worked with an allocator before, essentially how it works is you add free space to it, and then when you allocate from it, it subtracts that free space from its existing free regions. So you're just taking away from the allocator rather than the allocator giving to you some free memory. You're basically saying, don't ever allocate this part of your space that you've been given until I tell you that it's free, or tell you to free it, or that's not going to be used anymore. And at which point it inserts it back into its list of free spaces. So this is all just, just wrapper code, basically. But I like that I can use a Rust enum in order to do this. Because it can only be one or the other, right? It's kind of like a union in C, except even better, because you can actually store stuff in it that's useful and not just risking memory safety the entire time. So, yeah, and so here's the reverse example of me using macros to implement code. I found this very useful. I've only been writing Rust for about a year now, and I just recently learned about macros like this, where you can give it a list of tokens or a list of identifiers or expressions. And it will just generate code for you. I find that very useful. So, I'm not going to go into details about how the allocator works. It's basically just it's a pretty dumb allocator, honestly. It'll try to find a chunk of free memory that contains the address that or the page that you're trying to allocate. And or the pages that you're trying to allocate. And then if it finds one, it'll split that chunk in two. And then it'll do a quick bubble sort to make sure all the chunks are in order or sorted by their start address. And and then it'll merge the chunks upon freeing. Yeah, so it's literally just all free does is you give it an allocation. I do distinguish between allocated versus unallocated versus even versus mapped pages in my operating system. They are distinct types. So and that was inspired by Theseus as well, where it ensures memory safety by making sure that you can't, use or like write to pages that aren't mapped. Although that happens all the time anyway, because that's just the reality of writing an operating system. but maybe I could take a look at Theseus source code and see how they handled that. I don't know. That's just something for me to do later. Anyway, so that's the allocator. Let's go back to here. Page tables. Okay, this is something that I've been wanting to talk about for a while, because me and page tables, we go way back, man. Like, hold up. So in k4dos, in this new version of k4dos, we have a few different paging constructs. We have an address space, we have a page table, and we have a page mapper. So an address space, let's look at that. An address space is literally just an independent frame of memory, physical frame of memory that is unique in that it basically just contains a page table. So that's a bunch of commented out code I don't need anymore. Get rid of all that. So, like I said, I'm going to be cleaning this out as I go. That's no reason why I'm doing this. So, whenever you want to create an address space, it just allocates a frame from the kernel. And it will zero out the bottom half and copy the top half from the kernel page table. Because in k4dos, the top half of memory is for the kernel, the bottom half is for user processes. This is just kind of how it works out. So all the kernel mappings are going to be needed to be accessed by any address space that the kernel can possibly switch to, or else it can't run its own code. It won't be mapped, So, give me 1 second. I'm going to turn on my fan real fast. It's getting a little warm in here because my laptop fan is kicking up. All right. So we have, methods and functions to get the current page table from the CR3 register. We can switch to CR3 register with the frame containing this address space. We can get a mapper into this address space. And then we have stuff to do forking for processes. So I just go over the rest of the memory module. Well, first let's go over paging. So in paging, we just have page tables, page table entries, standard stuff for an operating system working on x86-64. Page tables are page aligned, just arrays of page table entries containing 512 entries. And 512 times 8 is 496. So that's how big they are. That's also their alignment, because that's important, or else Intel will personally come to your house and fire you. Or shoot you or something, I don't know. So, and we can access the next page tables based on certain entries. So if this is a level 4 table, we can access a level we can access a level 3 table, or create a level 3 table if it doesn't already exist by allocating a new frame. So pretty simple stuff, standard stuff at least. And then we have our mapper, and the mapper is able to actually take a page table, actually borrows a page table with a lifetime, and it can do all things like page translation, address translation, mapping pages, resetting flags on pages, unmapping pages, stuff like that. Pretty useful for doing stuff with memory in the heap. Speaking of the heap, let's go back to our module here. So after this, after we set up the kernel page table, we set up the kernel heap, which is literally just a matter of allocating some pages, allocating some frames, mapping them, and then adding them to the global allocator, which I use a global alloc. What am I using for that? Locked heap. I think it's a buddy system allocator. Yeah, it is. So thanks to that. Shout out to that crate for making k4dos possible, because I don't know how to implement an actual allocator that doesn't just allocate chunks of pages. So we convert those to heap allocated once the global heap allocator is set up. Set up syscalls, and that's just writing a bunch of stuff to MSR registers. Our syscall handler, our stuff from the GDT. I'm not going to go over anything about the GDT or how syscalls work or any of the x86 internal stuff. There's plenty of resources out there if you want to learn about that kind of thing, but I'm just going to kind of skim over that kind of stuff because honestly I've had really bad experiences with it. I don't want to talk about it. Also, it's just really technical, and it's not stuff that I've done. It's just stuff that I have to do in order to get this all working. So, load GDT, our actual GDT. We do have a per CPU structure right here that contains each individual CPU core will contain its own test or its own TSS. It'll have a pointer to its some extra data that it needs, like storing a kernel stack pointer for syscalls and its own GDT. And then I'm able to get that as a mutable static reference, mutable static borrow. So I should add an asterisk there and say that I don't actually support multiple cores in k4dos right now. That's something that I want to get to in the future, but I would have to set up ACPI and MADT tables and all that, and I don't even know how any of that works right now. I'm literally just running on one core with a really dumb interrupt chip emulator. I'll get into that with IDT, but no APIC, no local APIC, no IO APIC, just a standard PIC. So, but it works for now, so I'm happy with it. So we set up our TSS, we set up our our segment registers. Still don't know if I need to load FS&GS with the kernel's data segment selector. That hasn't caused me any issues yet, so I'm gonna leave it like that. But that might be something I need to do. I need to do more research into that. So get rid of all that. So anyway, with IDT, interrupts are handled by just so when Lamine boots my kernel, it'll have all the PIC programmable interrupt chip. It'll have all its interrupts masked, so I actually need to unmask them. And then I also set up the timer interval using some IO commands or IO instructions. So I can unmask an IRQ and I can mask an IRQ. This is my big interrupt handler match function. So I match on the vector and it does a bunch of stuff. So I have a macro to implement interrupt handlers. This is the assembly code for that. These are just macros to, push and pop a bunch of registers in the same order every time. So I quite enjoy writing the assembly code, honestly. It is very interesting, I guess. It kind of tickles my brain. It's almost therapeutic. Like, it's like, oh wow, I'm communicating directly with the processor. That's kind of cool, right? So no compilers, no nothing. It's just pure raw assembly code. So it's something cool about it to me, So you have code here to initialize the local APIC, but I have all that disabled right now. So after interrupts are initialized, I initialize the file systems. So I only support one type of file system right now. I only have one kind of driver or loader list, implemented right now, and that's for initramfs. I can actually go in here and show you the loader. This is very much taken from Kerla code. But I did, adapt it to how I was running my operating system. But it's a initramfs parser, and it will chew through those bytes and iteratively create a root file system from the inodes that it sees inside of the initramfs image. So it supports symlinks, supports directories, it supports files, of course. So initialize initramfs. All right, so this is where the bulk of my work has been lately. It has been in the task scheduler, the task system, and then syscalls. So when we initialize the task scheduler, let's see here. Yeah, so tasks are pretty darn complicated. Tasks, some people call them processes. I call them tasks and k4dos just for the sake of keeping everything brief, I guess. A task can have, so it's an architecture specific section to it that I'll go over in a bit. Tasks can be of having various different states. What was I going to say? Virtual memory management has been a pain in my side. So let's see, I'm always kind of overwhelmed by like all this stuff. Going over 8,000 lines of code in what has it been 30 minutes has been a lot on me. So, but either way, just to kind of skim through the rest of it, we can create an initial task. We can load ELF binaries. They have to be statically linked with no relocations or no PIE, anything like that. So, and going over that, we can do the standard forking exec of Unix type operating systems. So, I might just make this into a part 2, where I talk about the task system, because that's a whole own beast of its own. That I put a lot of work into that lately. But real quick, let's give a demonstration. I think we're overdue for a demonstration of the code. So, first thing I need to do, I'll show you the build process. It's pretty straightforward. I need to make sure I run setup externals, so I can make sure everything's copied into the initramfs image. I am using BusyBox. as like a source of like my core utils and all that. And I actually can run the BusyBox Ash shell on my operating system. I might show you that if I feel like it. But we go cargo run. Cargo will take care of building the entire kernel for us. And then we need to scroll up a little bit and see which terminal we are running on. I believe we are on, yeah, PTS 7. So we're going to minicom into that serial port. We're going to start debugging. And you're going to see a lot of log messages pop up. Oh crap, why are you doing that? Okay, let's just get rid of all these exceptions or breakpoints. Alright. So now if we go over here, we have a shell. This is my cache shell that I've been writing. And we have a few commands we can do from here. First thing is we can ls. And we can see, well, first of all, we can see that we're in root. We're in just the /root. So, cd into bin, and see we got all these programs in here from the netram fs image. This is mostly BusyBox stuff. Cd back, user bin, show you all the programs that we have in user bin. And of course that doesn't work. Right, give me a sec. But you get the idea. Let's actually run it this time with the BusyBox hash shell as the interpreter, or as a init process. See how that works. This should work. Yep, there we go. Of course we can't clear because we haven't done that yet. Okay, well, it's a little broken still, but you know, we have a shell that does a few things. The cache shell is really just I've only recently started working on it, so hopefully if I make a part 2 to this video, then I'll be able to show you some more functionality that I've embedded into it by then. But there we go. So yeah, this has been about a week of work to get this all up and running, although it's really been about 5 or 6 months of learning about this kind of thing in order to get this done in a week. So now I'm going to crash my operating system by trying to exit the init system. So I'm just going to terminate that. But yeah, anyway, thank you all for watching. I probably am going to make a part 2 to this because I do want to go into more about the init or the task system, the scheduler, how all that works. I've got preemptive task scheduling up and running, where it preempts in its own kernel thread. It also pulls the serial in its own kernel thread. So yeah, thank you all for watching. Let me know if you have any questions or comments in the comments. I'll see you all next time. See ya.